The resistors are the most common passive component in electronic circuits. A resistor is manufactured in a specific value of ohms. The purpose of using a resistor in circuit is either to limit the current to a specific value or to provide a desired voltage drop. The power rating of resistors may be from 0.1 watt to hundreds of watts. There are 4 types of resistors: wire-wound resistors, carbon composition resistors, metal film resistors, and carbon film resistors. Wire-wound resistors are made of nickel-chrome alloy wrapped around an insulating core such as ceramic porcelain, bakelite, pressed paper, etc. Wire-wound resistors are used for high current applications. They are available in wattage ratings from 1 to 100 watts or more. One type of wire-wound resistor is called as fusible resistor, enclosed in a porcelain case, is designed to open the circuit when the current through it exceeds certain limit. Carbon composition resistors are made of fine carbon or graphite mixed with powdered insulating material as binder in the proportion needed for the desired resistance value. Carbon resistance elements are fixed with metal caps with leads of tinned copper wire for soldering the connection into a circuit. Carbon resistors are available in values of 1 ohm to 22 mega ohms and of different power ratings. Metal film resistors are manufactured by 2 processes. Thick film resistors are pasted with metal compound and powdered glass, which are spread on the ceramic base and then baked. Thin film resistors are processed by depositing a metal vapor on ceramic base. Metal film resistors are available from 1 ohm to 10 mega ohms up to 1 watt. In carbon film resistors, a thin layer of carbon is deposited on the ceramic base or tube. A spiral groove is cut over the surface to increase the length of the foil. Carbon film resistors are available from 1 ohm to 10 mega ohms up to 1 watt. All the 4 types of resistors are coated with synthetic resin to protect them against mechanical damages and climatic influences. Resistors are specified normally with the 4 important parameters: types of resistor, nominal value of the resistors in ohm or kilo ohm or mega ohm, tolerance limit for the resistance value in percentage, loading capacity of the component in wattage. Resistors can also be classified with respect to their function as fixed resistors, variable resistors. In fixed resistors, the nominal value is fixed. These are provided with a pair of leads. Variable resistors are those whose values can be changed. The resistance value can be set at the different levels with the help of sliding contacts. These are known as potentiometer resistors or simply potentiometers. It is provided with 3 terminals. They are available with carbon tracks and wire-wound types. Trimmer potentiometers can be adjusted with the help of screwdrivers. Special resistors are also produced whose resistance varies with temperature, voltage, and light. In PTC resistors, as the temperature increases, the resistance increases non-linearly. In NTC resistors, as the temperature increases, the value of resistance decreases non-linearly. In VDR resistors, the resistance falls non-linearly with increasing voltage. VDRs are used in voltage stabilization, arc quenching, and overvoltage protection. LDR is also known as photoconductors. In LDRs, the resistance falls with increase in intensity of illumination. The LDRs shall have an exposed surface to sense the light. They are also used for measuring the intensity of light. Commercially, the value of resistance and tolerance value are marked over the resistors by color codes or letter and digit codes. There are 4 bands of color. The first band shall be the one nearest to one end of the component. The first 2 color bands indicate the first 2 digits in the numeric value of resistance. Third band is the multiplier. The fourth is tolerance value. If the color band on a resistor are in the order red, violet, orange, and gold, then the value of resistor 27 multiplied by 10 to the power of 3. The value of the resistor is 27,000 ohms with plus or minus 5% tolerance. For less than 10 ohms, the third band will be either golden or silver. Large value resistance are expressed in kilo ohms and mega ohms, represented by letters K and M. In letter and digit code system of coding, numbers and letters are used. We can measure the value of the resistors by using a multimeter or an ammeter. This is a ceramic fusible resistor. The value printed on it is 10 ohms, 10 watts. This can be checked with a multimeter in ohms range. We select 200 ohms in the meter because the resistor's value is 10 ohms. Now we touch both ends with multimeter probes. The meter indicates 9.6 volts. The code value of the resistor is 10 ohms and tolerance is plus or minus 5%. The measured value is 9.6 volts. The resistor is good. A capacitor is an electrical device consisting of 2 parallel consecutive plates separated by an insulating material called the dielectric material. Connecting leads are attached to the parallel plates. In a capacitor, the electric charge is stored in the form of an electrostatic field between the 2 conductors or plates due to the ability of dielectric material to distort and store energy while it is charged and keep that charge for a long period or till it is discharged through a resistor or wire. In the neutral state, both plates of a capacitor have an equal number of free electrons. When the capacitor is connected to a voltage source through a resistor, the negatively charged electrons are removed from plate A and equal numbers are deposited on plate B. Plate A becomes positive with respect to plate B. The current enters and leaves the capacitor, but the insulation between capacitor plates prevents the current from flowing through the capacitor. The ability to store energy in the form of electric charge is called capacitance. A farad is the unit of capacitance, and a coulomb is a unit of charge, and volt is a unit of voltage. Capacitance is mathematically expressed C equal to Q over V. The capacitance of a capacitor is determined by 4 factors: area of the plates, distance between the plates, type of dielectric material, temperature. The dielectric area is increased, the amount of energy stored in the dielectric material is increased, and the capacitance also increased. The strength of electric field between plates decreases when the distance between plates increases. The ability of a dielectric material to distort and store energy is indicated by its dielectric constant, represented by letter K. In ceramic capacitors, the discs are made by using ceramic as an insulator with a silver deposit on each side of the plates. Mica capacitors consist of alternate layers of metal foil and thin sheets of mica. The metal foil forms the plate, with alternate foil sheets connected together to increase the plate area, thus increasing the capacitance. Electrolytic capacitors are polarized so that one plate is positive and other negative. These capacitors are used for high capacitance values over 20,000 microfarad. Electrolytic capacitors are available in 2 types, aluminum and tantalum. One particular point you must always remember about the electrolytic capacitors is that one end is positive and the other end negative. Since electrolytic capacitor is polarized, the positive plate must always be connected to the positive side of a circuit. Be very careful to make the correct connection and to install the capacitor only in a DC, not in AC. Special electrolytic capacitors are manufactured for use in AC circuits. These are listed as non-polarized. An AC electrolytic capacitor is really 2 electrolytic capacitors packaged in a single container. There are several types of plastic film capacitors and older paper dielectric capacitors. Variable capacitors are used in a circuit when there is a need to adjust the capacitance value either manually or automatically. A capacitor is constructed with several plates that mesh together. One set of plates can be moved relative to other, thus changing the effective plate area and the capacitance. The movable plates are linked together mechanically so that they move when a shaft is rotated. Trimmers and padders are adjustable capacitors. They have screwdriver adjustments and are used for very fine adjustment in a circuit. This is an electrolytic capacitor. To check it, we select a range of 200 ohms in multimeter. we have to check twice by changing the multimeter probes. We get some reading in the multimeter and it disappears. Again, changing the probes in the capacitor terminal, we get some reading and it disappears. This capacitor is good. We are checking another capacitor. The multimeter shows close to 0. The capacitor is short. Here we are going to see the procedure for testing the capacitor for charge and discharge. Initially, touch both leads of the capacitor with a voltmeter. If there is any deflection, contact both leads through a resistance for sufficiently long time. Do not touch the capacitor leads by hand. High voltage retained by a charged capacitor will give a shock. Form the 12-volt circuit for testing the capacitor. Keep the switches open.
Two switches S1 and S2 are in closed positions. S1 is connected to a 12-volt battery. S2 is connected in series with the ammeter. There are 4 resistors of different values connected in series with a 12-volt capacitor. Now, we are going to close the supply S1 and S2. Now, we will observe the deflection in ammeter and voltmeter.
Record the deflection of the ammeter at the instant the switch is closed to position 1. Observe the voltmeter reading at equal intervals of time, at least 4 readings from 0 to the maximum deflections to be taken. Record the time and voltage. Repeat the steps by changing the value of the series resistance. Open the switch and observe the voltmeter reading for 5 minutes. Close the switch to position 2 and observe the voltmeter and ammeter readings. Repeat the test for different values of capacitance rated for different voltages. The testing voltage should be nearest to the voltage rating of the capacitor. Keep the ohmmeter selector switch at the higher range. Step 1. Discharge the given capacitor. Step 2. Connect the ohmmeter to test the capacitor and observe the meter deflection. While testing the polarized capacitor, the positive terminal of the capacitor is to be connected to the positive terminal of the ohmmeter and negative terminal to the negative terminal of the ohmmeter. If the ohmmeter indicates some resistance, there is some leakage, no deflection. Open. Deflects and return back slowly. Capacitor in good condition. Continuously shows 0 reading. Short. The surface at which these materials meet is a p-n junction. Diffusion occurs when p and n materials are joined together. Some electrons in the n material near the junction are attracted to the holes in the p material, thus leaving holes in the n material. The diffusion of electrical charges produces a potential difference in a small area near the junction. As a result, the material will conduct in one direction but not in the opposite direction. For this reason, the area in which this EMF exists is called a barrier. The positive terminal is connected to the P side and the negative terminal of the DC supply is connected to the N side of the junction. The positive terminal for the battery attracts electrons from P material, leaving excess of holes. Because electrons are drifting away from the junction, the excess holes tend to accumulate near the junction. At the same instant, electrons from the negative terminal of the battery are attracted to the less negative N material of the diode. This action overcomes the barrier at the junction and allows the electrons to move into the excess holes of P material. The result is a continuous flow of electrons in one direction. The voltage required to move the charge carries in forward bias conduction called the barrier voltage. The P side is connected to the negative and N side is connected to the positive terminals of the supply. At the same instant, a shift in electrons in the P material causes the positive holes appear further away from the junction near end of the diode, which is connected to the negative terminal of the battery. This action produces a wide barrier at the P-N junction through which the electrons cannot flow. But a small current leakage may, however, occur. The current, the forward direction increases rapidly upon reaching the forward voltage VB, which is known as the barrier potential or the junction potential. The behavior of the P-N junction is limited by the maximum forward current, as too much of current may destroy a diode due to the excess heat generation. The material. The diode is made of doped semiconductor material. This could be silicon or germanium or selenium. This is important because the cut in voltage depends upon the material the diode is made of. For example, in germanium diodes, the cut in voltage is around 0.3 volt, whereas in silicon diodes, the cut in voltage is around 0.7 volt. The diodes are printed with a type number. When this type number is referred to in the manufacturer's manual, the detailed specifications for a particular type number of the diode can be obtained. 1N is used as a prefix for semiconductors with one junction. For example, all 1N components refer to diodes because diodes have one junction. Components in the pro-electron system have 2-letter and numeral code for consumer devices. Example, BY27 and so on. 3-letter and numeral code for industrial devices. Example, ACY17 and so on. The first letter in the pro-electron type code indicates the type of semiconductor material used in making the device. The second and third letter indicates the applications of the component. The numerical after the second or third letter is the code number of its detailed voltage, current and temperature specification. Based on their current carrying capacity, power handling capacity, diodes can be classified as low power diodes can handle power of the order of several milliwatts only. Medium power diodes can handle power of the order of several watts only. High-power diodes can handle power of the order of several hundreds of watts. For checking diodes, set the meter at the diode symbol 2000. The black probe is negative, the red probe is positive. With this, we test the diode. In a diode, the ring indicates cathode, which means negative. The other side is positive, that is anode. Diode only works by forward bias. Forward bias means it gives positive to anode and negative to cathode. Connect the negative probe to cathode, positive probe to anode. Now we observe some reading. The diode is working condition. This is called forward bias. Same time, now we change the terminal leads and connect positive probe to cathode and negative probe to anode. No reading in the meter. This is reverse bias. The diode is in good condition. Transistors are the semiconductor devices having 3 or 4 leads or terminals. Transistors are mainly used for enlarging or amplifying small electric or electronic signals. The circuit which uses transistors for amplifying is known as a transistor amplifier. One other important application of transistors, its use is a solid switch. A solid switch is nothing but a switch which does not involve any physical on or off contacts for switching. Transistors can be thought of as 2 p-n junction diodes connected back to back. Some important advantages are very small in size, light in weight, minimum or no power loss in the form of heat, low operating voltage, rugged in construction. Like in diodes, transistors can be made using silicon or germanium. Silicon transistors work better over a wide temperature range compared to germanium transistors. Transistors data books give information about the semiconductor used in any particular transistor. Based on the way P and N junction are organized, both NPN and PNP transistors are equally useful in electronic circuits. However, NPN transistors are preferred for the reason that NPN has higher switching speed compared to PNP. Low power transistors, also known as small signal amplifiers, are generally used at the first stage of amplification, in which the strength of the signal to be amplified is low. For example, to amplify signals from a microphone, tape head, transducers, etc. Medium power and high power transistors, also known as large signal amplifiers, are used to achieving medium to high power amplification. For example, signals to be given to loudspeaker, etc. High power transistors are usually mounted on metal chassis or on a physically large piece of metal known as heat sink. The function of heatsink is to take away the heat from the transistor and pass it to air. Inside a transistor, there are two p-n junctions connected to each other. Outside a transistor, one can see only three leads: base, emitter, and collector. These are all called transistors. We see the collector. The center one is the base. Other side is the emitter. There are some numbers written on it: AC 127, BF 194. The first letter A, germanium transistor. The letter B indicates that it is a silicon transistor. The second letter C indicates that it is a low frequency transistor used in audio frequency. If the second letter is F, it indicates high frequency amplifier, and it is used in IF or RF sections. Let us see how to check a transistor. As already told, there are three legs. The right side is the collector, center is the base, the emitter is on the left side. Now we keep the negative probe in base and connect the collector with a positive probe. There is some reading. Same way, connect the emitter. Now we get the same reading. So we get two positive and one negative terminal. So this is PNP transistor. Now we connect positive probe to the base and connect the other terminals with negative probe. No readings. This is good. We check another transistor. Now we keep positive probe on the base and connect other terminals with negative probe. We get some reading. This is a NPN transistor. We change probes, and now we get no reading. This is good. Most of the equipment, both an entertainment and professional, need DC voltages for operation. The power supply converts AC supply voltage into DC. Diodes are used as rectifier in a power supply circuit. This simplest form of AC to DC converter is by using one diode, such as AC to DC converter is known as half-wave rectifier.
This is a step-down transformer, center taped. There are two diodes, D1 and D2. A resistor is connected. A full-wave rectifier.
Connect AC mains to the board and switch on mains. Measure and record the mains voltage and transformer secondary voltage V. AC input to rectifier. Calculate and record the expected DC voltage across load RL using the formula. Measure and record the rectified DC voltage V DC across load RL using multimeter. Record the difference in the calculated and measured values. Construct a full wave rectifier circuit. Switch on the circuit. Measure the AC input voltage V to the rectifier across the center. Tap at any one end of the transformer and record it. Calculate the expected DC voltage VDC across load RL. Measure the rectified output across load RL. Calculate and record the difference in the calculated and measured VDC values.
This circuit is called bridge rectifier, consists of 4 diodes. D1 anode and D2 cathode are joined here. D3 cathode and D4 anode are joined here. These 2 pins are connected to transformer secondary. Load R is connected. This is bridge rectifier.
Switch on the circuit. Measure and record the AC input voltage to the rectifier. Calculate the expected output DC voltage VDC across load RL. Measure the DC output VDC across the load RL and record it. Record the difference in the calculated and measured values. A printed circuit board is a circuit on a board in which the interconnecting wires are replaced by conducting copper stripes, generally of copper, which are attached or printed or etched onto the board. The base materials for making PCB is known as copper-clad board, in which a thin layer of copper is deposited on one side or both the sides of an insulating board. The insulating board is generally made of phenolic or paper or fiberglass or epoxy. These boards are also called copper laminate boards. The required circuit pattern on the copper laminate board is made by a process called etching. Etching is a process of removing portions of a metal foil, leaving behind only the required portions of a metal foil. An etched board with only the required stripes of copper necessary for component interconnection. The areas of copper with a hole at the middle for making solder connections of the component leads. These are called pads. Holes are drilled in the center of the pads for inserting the component's leads. The copper area around the hole of a pad is referred to as the annular ring. Pads can have any shape, such as square or rectangular or elliptical, and so on. Rectangular pads are generally used for input or output connection. Square pads are used in places to indicate the first pin of the integrated circuits. Printed circuit boards can be made by one of the two methods: drawing the circuit pattern outline on a graph sheet, tracing them onto copper laminate board, and etching them manually using etchants; making artwork of the circuit using artwork tapes and pads, or using computerized methods, and using photographic method of exposing the artwork on the laminate and etching them either manually or through automated methods. The schematic is drawn on a plain paper with a rough plan of the component placements and interconnections. The dimensions of the components to be mounted on the PCB are collected. Lead bending dimensions are noted. The schematic is redrawn on a graph sheet with a proposed component placement. Copper track dimensions. This gives the solder side PCB layout. Etch resist links are chemically resistant materials used to mask the areas of copper foil on a copper laminated board. When etched using enchants, these masked areas are protected from the chemical action of the etchants. Hence, copper only in those areas not masked gets etched. Once the required portions on the copper foil side of the laminate is painted or masked and dried, the next step is to remove the copper present in the unmasked portions of the laminate. This process is known as etching. Etching is done using any one of the following chemicals: alkaline ammonia, sulfuric hydrogen peroxide, ferric chloride, cupric chloride. While preparing the etching solution, concentrated ferric chloride solution or powder is mixed with lukewarm water. After cleaning the board using water and dried, the etch-resistant ink or paint on the layout pattern is removed using solvents such as thinner or petrol. The clean board will then have bright copper stripes and pads only in the required portions representing the circuit. The next step after etching and removing and mask or paint is to drill holes of required diameter in the pad center for inserting the components, input or output, and VCC and ground connections. Extra care is to be taken while drilling holes because carelessness while drilling may peel off the pad area of the copper. A typical component side of a PCB with the components marked on it. The standard procedure of component marking is to mark either the symbol of the component along with its code number. Dust, oil, oxide layer, or protective coating on the component leads must be removed well prior to soldering. If not, the adverse effect may result in dry soldering or improper wetting. In addition, the excessive heat due to prolonged heating may peel off the copper pad pattern, making the whole PCB unfit for use. The shape to which the component leads are to be sent has two aspects: the manner in which the component is to be mounted, to reduce the stress exerted on the component by a variety of forces, depending on the type of component lead on the space available on PCB. Components can be mounted either vertically or horizontally. The order in which different types of components are to be soldered on a PCB is very important, especially in manual soldering. The suggested order is: first, connectors and fuse holder; second, all high voltage resistors; third, all low voltage resistors. Fourth, all capacitors in the order of heavy to light. Fifth, active device such as diodes, transistors, ICs in the order. Soldering irons are available in different wattage ratings, starting from 10 watts to several hundred watts. The wattage of a soldering iron specifies the amount of heat it can produce. As a thumb rule, higher the physical dimension of the workpiece, higher should be the wattage rating of the soldering iron. To ensure that the joint is heated to the required temperature ideally, the area of the tip face should be approximately equal to the area of the joint to be soldered. The tip should be long enough to allow easy access to the joint. The tip should not be too long, as this may result in the low temperature at the tip's working face. For electronic soldering applications, solder of tin and lead of 60/40 proportion is used. For electrical purpose, resin core soldiers are used. For ease of application, the flux used in addition to the cored flux in solder should be in paste form. The soldering bit tip should be cleaned, heated and tinned before starting the soldering work. Before joining two pieces of metal by soldering, the joining surfaces should be cleaned to remove foreign matters over the surface. Do not apply too much flux on a joint in one place. Apply a small amount of flux around the joint. Place the iron tip at the joint such that the tip gets maximum contact with parts to be jointed. Slowly feed the solder into the joint, starting close to the soldering tip and moving towards the edge of the joint. Continue applying the solder to the joint until complete wetting of the joint has been achieved and the joint has a concave fillet. After enough solder has been applied and solder removed, keep the soldering iron tip on the joint for a moment to ensure that all the flux on the joint has reached the soldering temperature. This will allow majority of the acids within the joint to break down, which otherwise will corrode the joint after a period of time. Generally, the time taken to make a good soldered joint is between 3 to 7 seconds from applying the soldering iron to and removing the soldering iron. Allow the joint to cool without assistance. Do not blow air from your mouth or from any other source to cool the joint. Forced cooling cools the joint much earlier than it has to, resulting in a dry and brittle solder joint, which will lead to mechanical and electrical defects of the joint. Do not move any part of the joint while it is cooling. This disturbs the chemical bonding taking place. Movement of the joint while it is cooling results in a dry joint. When a solder joint is made, the amount of flux applied should be just sufficient to make a good joint. But, quite often, there will be brown waxy substances left on the joint. This is nothing but the flux residue. In its original state, this residue is corrosive. Hence, the flux residue or excess flux must be removed from the joint before soldering can be considered as complete. Removal of flux residue requires the use of solvents. The type of solvent depends on the flux used. The surface of a correctly soldered joint will be glossy, silvery, and uniform in color. The surface texture of a correctly soldered joint will be smooth, even, and non-grainy. There shall be no signs of pitting on the surfaces of the solder. Temperature defects are caused by excessive or insufficient heating of the joint during the soldering process. It is better to practice bending, trimming and soldering various types resistors. We are going to see the electromagnetic induction. Inductance is the magnetic property of an electrical circuit or device to oppose any change in the magnitude of current flow in a circuit. Devices which are used to provide inductance in a circuit are called inductors. Inductors are also known as chokes, coils, and reactors. Inductors are usually coils of copper wire. The effect of induction is based on the principle of Faraday's laws of electromagnetic induction. When an alternating current flows in a conductor, the current periodically changes its magnitude and the direction. As such, the magnetic field it produces also changes. At any instant, the direction of the magnetic field is determined by the direction of the current flow. With one complete cycle, the magnetic field around the conductor builds up and then collapses. It then builds up in the opposite direction and collapses again. When the magnetic field begins building up from zero, the lines of force or flux lines expand from the center of the conductor outward. As they expand outward, they can be thought of a cutting through the conductor. The inductance of an inductor is primarily determined by four factors: type of core, relative permeability of the core materials, number of turns in the coil, spacing between turns of the coil, length of coil over core, cross-sectional area of the core, diameter of the coil or core. If soft iron is used as a core material instead of hardened steel, the coil will have more inductance. If all the factors are equal, an iron core inductor has more inductance than an air core inductor. This is because iron has a higher permeability, that is, it is able to carry more flux. With this higher permeability, there is more flux change and thus more EMF for a given change in current. Adding more turns, an inductor increases its inductance because each turn adds more magnetic field strength to the inductor. Increasing the magnetic field strength results in more flux to cut the turns of the inductor. When the distance between the turns of wire in a coil is increased, the inductance of the coil decreases as the turn insulating material. Normally, the winding is done over a former made of PVC-based material and inserted over the core. If heavy wire is used in making the inductor, a bobbin is actually not needed. The rigid loops of wire support themselves. When a magnetic core is not used, the inductor is usually referred to as an air core inductor. The inductor is used to induce a momentary high voltage to fire the lamp. Prepare a wooden former. A slight taper towards one side to enable the wound coil to be removed easily. Cut the leatheroid paper 7 millis, a width of 62 millimeters, and wrap tightly twice around the bobbin of the former and fix it with sellotape. Measure the available winding wire and choose the 27 SWG super enameled copper wire. Insert the ampere sleeve 2 mm in the starting lead and fix it properly with sellotape along with 2 twine threads. With the help of the winding machine, wind 1150 turns uniformly, layer by layer on the bobbin. Exercise care to avoid formation of knots or sharp bends or nicks in the winding wire. Insulate each layer with fish paper. Provide sufficient end leads. Insert the ampere sleeve 2 mm in the ending of the winding wire and fix it on the bobbin with sellotape. Tie the coil with the help of twine threads securely so that the layers of turns are in position. Wrap one layer of thin insulating adhesive tape around the coil. Remove the coil from the former. Repeat steps and make another coil. Insert the given coil lamination one by one alternatively into the coils without damaging the coil insulation. Check the individual coils for continuity and soundness of insulation with respect to the core using a test lamp in AC 240 volts. Continuity should be okay. Insulation resistance should be more than 1 mega ohm. Measure the resistance of each coil with the help of an ohm meter. The resistance of each coil should be around 27 ohms approximately. If there is a variation, investigate the reasons. Connect the two coils in series. Use the right-hand grip rule to determine the magnetic polarity of the coils before series connection of coils is done. Assemble the core and winding inside the metal cover. Disconnect the choke from the tube light fitting and remove it from the base. Fix the newly wound choke in place of the old one and connect the choke to the tube light circuit. The instant start or quick start method of starting fluorescent lamps consists of an auto transformer connected across the tube. On the instant the switch is on, a very high voltage in the order of 5 kV is produced by the auto transformer across the cathode. This high voltage breaks down the resistance of gas between the cathode and strike the arc. The arc quickly heats up the filament in the cathode, which then supplies electrons to sustain the arc. The fluorescent lamp, designed for instant starting, has only one terminal at each end. It has a filament type of cathode, and the ends of the filament is shorted and connected to the single pin. Therefore, the need for separate starters is eliminated. The tube diameter of the instant start tubes is smaller than the preheat tubes. This is power cord. This is circuit board. Holder for CFL. This is compact fluorescent lamp. This is circuit board for CFL. It has 4 wires, 2 wires for AC in similar color, and other 2 wires for CFL tube. The holders have 2 pins for power supply and 2 holes for inserting CFL tube. 2 pins, 11 watt CFL tube. Look for the most common physical faults such as broken wires, cracked circuit boards, and dry solders and burnt out components. Smell for hot or burning components. Feel with the fingers for unduly hot components. Learn the operation of the system to be repaired with the help of its block diagram and its input and output specifications. Observe the symptoms produced by the defective system and determine which section or function should produce the symptoms. Testing and replacing defective components. When the probable defective section has been diagnosed, components should be checked in the order given below: high voltage or power passive components. Such components are resistors, capacitors, transformers and coils, etc., which handle large amount of voltage of power. They are found in power supplies and output circuits. So far, we have seen the various components and their functions of an electronic choke. We have also seen the process of making a PCB and assembling of CFL. I hope you would have understood this subject in a better way. Thank you.
Good morning, India! My young friends, today I want to tell you, I want to tell something to the world's youngest force. I want to say that whether it is blazing sun or the fierce lightning, we the youth shall face it head on. Or whether it's a cyclonic storm, for whatever